Today we're going to demonstrate the DOS-68 operating system running on this Southwest Technical 6800 computer. DOS-68 was introduced by a company called Smoke Signal Broadcasting in December of 1977. It came out to support a new disk system that they introduced for the 6800 computer at the exact same time. Now I find this operating system significant because in my opinion it's the first real operating system for the Southwest Technical 6800. It was not just another North Star DOS clone like both Southwest and Percom had done just a few months earlier. Excuse me. In fact, it was a lot more like the Flex operating system that you've seen me demonstrate numerous times in other videos in this series. In fact, it's so much alike that you cannot help but assume there was some commonality in the development there. In fact, I'd always assumed that DOS-68 stole or was based on Flex. But in reality, now that I've been digging into this further, DOS-68 came out a good 5 months ahead of Flex 1.0. So in reality, Flex was probably based on some things that were done for DOS-68. And in fact, there is some commonality there, and I'll address some of that maybe in another video so we can learn more about that. All right, so the disk system came with this disk controller you see here on the left. The one on the left is the original disk controller. It's called the BFD-68. I think that stood for Basic Floppy Disk. And about a year later, this one on the right, version A, came out. Now these look substantially different, but in reality, they're basically the same thing. The main thing they added in version A was they added a fourth drive select, up from 3 on the original, and then they also added a side select signal so that they could take advantage of the new double-sided drives that were coming out. Other than that, there's really not much difference other than this obvious difference of connectors across the top. This connector on the far right is identical to this connector. This connector in the middle was to make it easier to hook to 50-pin standard of the 8-inch drives. Previously, you had to make an adapter going from the 34-pin to the 50-pin externally in order to use 8-inch drives with this. But the board, nothing in the A added new capability for 8-inch. In fact, both of them had to be updated. Different crystal run at twice the speed, and they had different components or tweaking them for the data timing of 8-inch, which is twice as fast as 5 1/4. Neither of them could do both at the same time. And then finally, they added this third connector to allow the 4 drive selects to be used with the 5 1/4-inch drives as well. The issue there was that Shugart only defined 3 drive selects on the 5 1/4-inch connector. So you couldn't address the 4th drive that they added the capability for with this board. So what they've done is on this connector, they added the 3rd and 4th drive select and mapped it to the 1st and 2nd drive select on the cable out to the drives. So you could put drives 1 through 3 here and drive 4 on that cable, or drives 1 and 2 here and drives 3 and 4 on that cable. All right, now both of these boards have a ROM on board that includes boot code and also includes the I/O routines that DOS-68 would call. So any hardware differences that there were hidden by this ROM because DOS-68 simply called that ROM to do its disk I/O. All right, to boot this system, you jump to this EEPROM, it's a ROM, at address 8020 to boot the disk. Now for those of you who have Southwest Technical 6800 computers or remember how they're designed, you're probably raising an eyebrow right now because at 8000, that is where the I/O bus you see there in the back is decoded. An entire 8K block from 8000 hex through 9F/FF is dedicated to the I/O space. So there's no way you could have a ROM for this card in that I/O space. Well, actually there was. In the end, they took advantage of the fact that every other 32 bytes in that 8K address space is not decoded. Nothing responds at all. And so in all of these 32 byte holes, they made this ROM appear, and then the I/O memory mapped I/O for using the disk controller hardware features was mapped inside those same holes as well. So what they achieved is basically an invisible board. It used no memory space for any standard board or application or software, and it used no I/O space either. So that's a pretty cool trick, in that this board basically had a ROM on it and full memory mapped I/O, but used no resources that anything else in the Southwest system ever used. Pretty cool trick. All right, so let's go ahead and get this closed up, and I'll hook up the drive cabinet and we'll start demonstrating DOS-68. This disk subsystem from Smoke Signal Broadcasting included the disk controller that we've been looking at. It came with a diskette containing DOS-68, and then it came with a drive cabinet that held 1, 2, or 3 5¼ inch ShoeGuard SA400s, at least in the beginning. Later on, they shipped some other brands of drives. Now, I don't have that original drive cabinet. However, it would have looked a lot like this Heathkit one here. Pretty much the same size. It had the drives on the edge, just like this cabinet. And then in the back was a power supply that provided power for the drives. Other than that, the cabinet was pretty much a passive unit. It had nothing to do with the actual operation of the disk interface or anything. All right, so let's go ahead and get this DOS-68 up and running. We'll go ahead and run with 2 disks today. There's the boot disk in drive 0. And we have a data disk over here in drive 1. Computer's already on. I'll reset it just to be safe. And we're going to be in SWAT boot. And so to boot this, like we saw before, we jump to address 8020. That's in the ROM on that card. And as soon as I hit the 0, then it will begin booting. Let me go ahead and get that drive in the screen. Whoops, typed it wrong. Try again. All right, so you can see the drive come on. And then over here, you'll see some activity in just a second. There we go. DOS is now up and running. And now it's out on the disk getting a file called start.up. That's a lot like an autoexec program in MS-DOS. And you see it ran another program called set to set some parameters about the related to the screen. And then it got a file called sysprint.bin and stuck that in memory. That is a print driver, and we'll actually use that in just a minute. All right, one of the first things you probably want to do is get a directory. That's the list command. And as we look at the output of this, we can see that we have 6 character file names and 3 character extensions. So that's a little bit less flexible than the 8 character file names that we're accustomed to, but that's still workable. All right, another thing that's interesting, you'll notice it grouped a whole bunch of files that have a $sign as an extension. That $sign extension is equivalent to a .com file in CPM or a .cpm file, a .cmd file in Flex. It is an executable file that you could run by just typing its name with no extension. And most of your operating system commands are part of this because they're what are called transient. So here's the list command that we just run. View is a way to look at text files. We have a rename command. You saw that set program run during the startup. Delete command, append combines binary files. We'll look at that in a minute. There's copy for copying files back and forth, a format command. This is not a link editor. This is how you point the system to the bootable system file. But most of your executable files here are related to DOS-68. But then you can also add your own programs to this if you want. For example, here's basic, here's an assembler, here's the editor. Not necessarily considered the operating system, but those are just commands you can run with those names. All right, to run a program that you don't put a $sign on, but is actually an executable program, for example, the output of the assembler is a .bin file. I have a hello world called hello.bin. You use the run command. So run is how you execute a program that doesn't have a $sign extension. So there's our hello world. If I rename hello.bin to hello.$, so for example, here's the rename command. It goes out and loads that from disk, runs it, which then does the rename for us. And now I can run hello just by typing its name. All right, like CPM and Flex, you can use drive designators to look at different drives and run things on different drives. It uses drive numbers just like Flex. So 0 was our boot disk, drive 1 is the second disk. So if I list 1, we can see what's over on drive 1. Here we're getting a directory of the second disk in our system. And this has Smoke Signal's Fortran on it. We'll demonstrate that in a little bit. All right, you can look at any file you want, text file with the view command. And I could say 1: let's look at this test.4. This is a Fortran source file. And with the 1: it's saying get it off of drive 1. And so here's a little Fortran program. And I can look at our hello world over on drive 0 by doing that. Now you've noticed I've not put the 0 in front of that. And that's because just like Flex, DOS-68, in fact, DOS-68 introduced the concept of a system drive and a work drive. and at power up, those are both set to 0. So at this point, no matter what I do, if I don't specify a drive designator, I'm going to get drive 0. All right, let's see, what else do we have here? All right, you can copy commands, copy them on the disk. You can copy them from disk to disk. So we'll do this, we'll run copy, and let's copy hello. And you can explicitly state that, for example, we'll copy hello.bin to 1 hello.$. All right, so this is all explicitly naming everything. As you might expect, you can do wildcards. Oh wait, I renamed it hello.$, didn't I? So let's copy 0 : hello.$ to 1 : You can do a shortcut. If you're going to name it the same thing, you don't actually have to explicitly put it over there. And of course here I could eliminate the 0 : You can copy an entire disk just by typing in, let's see, wait for this to finish. Not really fast, by the way. All right, so if I wanted to copy everything in drive 0 to drive 1, that would be the syntax, or a comma in there is fine as well. But anyway, so I should have a 1.hello, so I can execute it by explicitly using the drive number, and there I get it. All right, binary files on this. We looked at source files like with the view command. So view, let's do it like again at hello.txt. That's our hello world program. Binary files are sort of like a S records from Motorola, except the difference is instead of using ASCII hex, it's in binary, so it's more efficient. But you still have the same concept of loading a segment of data anywhere from 1 to 255 bytes long, and you say where that segment goes, just like S records. So for example, the find command is used to find out where a program loads and executes. So I want to do list $. If I say find list $, you can actually see the segments that comprise it. So it has a segment from CD80 through CF66. Well, that could be multiple segments, but they're all contiguous, so it lists them as one. And then a separate segment at 6FC. So you can see there's a hole there of 8 bytes, and then it knows where the load address is as well. So this can be, there's a bit of overhead with this, about 1.5% overhead to have this record address and account in there. But it also could end up saving space in that holes don't actually end up taking any space like it does with CP/M, where it just is contiguous the whole way. All right, so another nice thing about this is you can actually combine disjoint files with what's called the append command. So for example, in these early days, we did not have an assembler that generated relocatable object code in the linker, but compiling or assembling a big program could be difficult. You might want to break that into multiple smaller programs, maybe that shared a common data area, for example. So what I've done just to illustrate this, but in miniature, is I made hello program. This is everything but the actual message, so this would be the code. Hello, oh, not list, that's flex, it's view. Hello program. So this is our hello world program, the code part, not the actual message. So we're going to refer to mdata at location 200. We're running at 100, but it's going to get data at 200, and that is in a separate file we assemble, and I call that hello data. And imagine that hello was 3 or 4 big programs, and then D was a large data area that all of them shared. So this loads at 200, and it actually has the message. So 2 completely separate binary files. The append command allows you to combine those. So I can combine hello data.bin with hello program.bin. Now this actually is going to combine this into this. So hello.p.bin will be the combination, and then it deletes hello.bin. Now in Flex, you put a third file that says combine this with this and make this third file. And don't destroy either of these, which is frankly a little bit safer, a little better in my opinion. All right, so now if we do the find on hello p.bin, you'll see that it's got a segment at 100 and a segment at 200 because we appended those 2 binary files. There's the program part and there's the data part. and there it runs like you want. I had a different message. This one says it's the split hello world. So that's how that's handled. All right, let's see if there's anything else we want to look at before we move on. One thing I don't like about List is that it has no wildcard capability. I do not have an option to not list everything. I can't tell it to do just dollar signs or just hello dot asterisk. It always is going to show everything. Now obviously I've paused the display here. You can define the pause character and then resume it. I just wanted to show you these two files. The DFM68O, that's actually an O, not a 0, stands for overlay, and DFM68O353, those are the disk file management routine overlays. So rather than make the operating system bigger and bigger, it puts some of the file management routines into overlays, the ones that aren't called as often. So when it needs them, it pulls them into an overlay area to run them. Now, of course, this does slow things down a bit, but it makes the operating system memory footprint smaller. Deleting files is in here, a few things like that. So any program that has to delete a file, for example, when we did the append up here earlier, it deleted a file. That slows it down a bit. When you exit the editor and it has to rename and delete files, it goes out and has to load these. That's a fairly slow process to exit that editor. All right. I forget how to resume it. There we go. All right, we have BASIC on here, so we can run BASIC. Now BASIC, they actually hired another company or used another company's and had them update it to work with DOS-68 to make their BASIC. This was to get themselves to market earlier, but make sure they had quality software. They only tried to use really good programs that they could find. This is written by a company called Computerware. And you can load, let's see, demo.base I think I have out there. So as you expect, you can load and save files, that kind of thing. Exit the DOS. We have an assembler out there. Let's assemble hello. It assumes a .txt extension. The assembler was provided by a company called Technical System Consultants. So was the editor. That's TSC. TSC is the company that wrote Flex and some other software for the Southwest. So by approaching TSC to develop an editor and assembler for them back in the middle of '97, they gave them DOS-68 and say, here, it's got to work with that. Here's our documentation. TSC was then very familiar with how DOS-68 worked and its internals. Then in turn, they used a lot of that when they created Flex a few months later. At least that's the only version of the story I can come up with. All right, so there's the assembly. You see it generated a listing as that went by. Another thing you can do is precede any command with a P to make it go to the printer. So for example, if I view hello.txt, it comes to the screen. If I precede any command with P, then what would have gone to the screen now goes to the printer. For example, you could do this with the assembler. You could say P and then assemble the file. The output of that assembly would go to the screen, to the printer. And you probably recall that P feature is in Flex as well. Again, there's a lot of similarities in how these two operating systems work. All right, let's go ahead and take a look at that second disk, and we'll take a look at the Fortran compiler that Smoke Signal made for this. Fortran for this machine was created in-house by Smoke Signal Broadcasting. So this is different than the editor, assembler, and different than BASIC, for example, where they used an outside software house for those programs. All right, so we've got the Fortran system here in the second disk. That's list 1. We're seeing what's on the second disk. And here you can see the Fortran compiler itself. Here's the linker that would be used to resolve references with the library over here. There's the Fortran library. All these LPs are related to line printer output. Their Fortran implementation gave Fortran its own line printer output independent of the print command you saw us earlier. And I guess I don't recall Fortran's details, but that was its default output as opposed to coming here to this console. So rather than go to a printer, I created a line printer that goes to the console for Fortran. And that's this LP con here bin. We'll load that later to get our output. All right, so this is a good time to use the system disk and work disk concept. I'll set work equal to 1. What this means is now it's going to go here to disk 1 to get anything that's an argument for a command, like the compiler or the linker, that kind of thing. So for example, if I say view test.fortran, this is the source file, view is going to come from the system disk, which is still 0. You notice view is not on this disk, it's going to get it from disk 0. Test.4 will come from here though, because that's the work disk and that's drive 1. All right, so now when we compile it, in fact, I wonder if I might need to get rid of the previous versions. Well, hopefully it'll ask me for it. So to run Fortran, it's not on drive 0, which is still the system disk. So I'm going to have to tell it explicitly to get it from drive 1. And test.4. So this runs the compiler now. Now this is a fairly long process. It takes about 2 minutes. This first delay here is just the time it takes to load the compiler off a disk. In the end, this whole system is not very fast, but I guess compared to paper tape and cassette or driving down to the computing center and dropping off a deck of cards for a compile and then coming back later, this was way faster than that. Okay, so it doesn't give me the option to delete it. It has to be deleted ahead of time, obviously. So delete test.rel, and again, delete's coming off the system disk, and it's going to the work disk to delete the relocatable code I had made from the past. And I also had the executable on the delete that. Right, so there you can see how system disk and work disk works. I have system commands still coming off of 0, but the commands are all referencing drive 1, which is my work disk. All right, so let's try this again. We'll now compile this. All right, so after it gets Fortran compiler is not on drive 0, so I have to explicitly put drive 1. So you're getting a good demonstration of the system disk and work disk features in DOS-68. All right, when you see this prompt come up here in a second, you'll know that the compiler's actually been loaded and now is running. Then once it starts running, this whole process takes about 2 minutes to compile this. So I'm going to go ahead and do a video cut, and I'll come back when this compilation is complete. All right, the compile is now complete, and at this point we need to run it through the linker in order to resolve references with the Fortran runtime library. So we'll run the linker. This is a bit shorter than the compiler, so it doesn't take quite as long to load. All right, first thing we'll do is load the file we just generated, which was test.rel for relocatable. And then next we're going to tell it to pull in the Fortran library with the lib command. And then finally after this we can specify the output file with the obj command, and I'll just call it test.bin. That'll be our executable. All right, now at this point it's going to resolve all the references, pull in all the code it needs from the Fortran library, and generate test.bin. Again, this takes a little bit of time, so I'm going to go ahead and do a video cut, and we'll come back when that's finished. All right, so that part is completed, and now we can just exit the linker, and now we're ready to run the program. Oops, I always forget to put the 1 on there. In Flex, when you do a listing or a catalog, it's called there, it does the work disk and not the system disk. Whereas in DOS, for example, this parameter still is got to be specified. All right, so we have our test.bin that we created, but it's going to go to the line printer output that is custom to Fortran. It's not the line printer output you saw previously. So I'm going to go ahead and load the lpcon.bin file that I created. This generates a printer that goes to the console. So now we can run test.bin, which is our Fortran program. Let me show you what it does first. Okay, so it assigns 3 to A and then writes A out through device 102 using the format in 10. So you'll have a 3 and a 3. Then it calls TED, which multiplies it by 2, and writes X, which is the result of multiplying A by 2, and prints those out and then stops. So now if we run it, we'll see your typical ugly Fortran scientific notation. All right, so there we have our 3 times 10 to the 1. 0.3 times 10 to the 1 is 3 and 3. Then we run it through the doubler. A is still 3 and X is now 6. All right, well that does it for this demo of DOS-68. Again, what I consider to be the first real operating system for the 6800. Flex followed after this and was very, very similar, borrowing heavily from DOS-68's design concepts. And it went on to be a more widely used operating system and therefore had more time to mature and develop new features.